Hello, everybody. It's Monday, February 23rd, and we were supposed to get a big storm today. I suppose it's still coming. It hasn't come yet. It's just about 1 o'clock, and I'm going to now record today's lecture, which I'll be posting in a little bit onto YouTube. So the next module we're going to be starting is Module 3, and Module 4, and it's about conjugated unsaturated systems. So let's take a look at this molecule here. We see that we have a lot of double bonds in this molecule. If we remember our valence bond theory, each of these carbon-carbon double bonds, the carbon is sp2 hybridized. So in this molecule, they're all sp2 hybridized except carbon number 5. It's sp3 hybridized, and so we have two different pi systems. We talk about this pi system as being conjugated. We have a double bond, a single bond, and a double bond, but the electrons are delocalized within this whole pi system. Over on this side, we have an isolated pi bond. It's just one pi bond, and it's not conjugated with this system over here. By conjugated, what we're going to see is that this pi system can communicate with this pi system. It's actually all one pi system. But over on the other side, we talk about this being an isolated pi system because it cannot communicate with this pi system over here. It's isolated from it because there's this sp3 hybridized carbon in between. So let's take a look. Let's get into this and see what we're talking about between these conjugated and isolated double bond systems. So a conjugated diene, our pi bonds are separated by only one single bond. Notice that all of our carbon atoms in this pi system, they're sp2 hybridized. So there's a p orbital in each of these carbons, and that's where the electrons are in the pi system. And those p orbitals are continuous amongst here. If we take a look at this one, here we have a diene as well. But notice now that we have sp2 hybridized carbons here and over here, but in between there's an sp3 hybridized carbon. So there's p orbitals that can line up here and here, but they cannot overlap because of this intervening sp3 hybridized carbon. And over here we have another different system. It's a cumulated diene, and notice now that our pi system we have two pi systems in a row. There's nothing in between. This carbon is sp2 hybridized, this carbon is sp2 hybridized, and this carbon is sp hybridized. Okay, these two, of course, are sp3 hybridized. But because this one is sp hybridized, it has two p orbitals that are going to be orthogonal to each other at 90 degrees. So let's see what we're talking about here. Here's our conjugated system. Notice now that those four sp2 hybridized carbons are all in a row, and the p orbitals can all line up, and we're showing that they can overlap. In our isolated diene system, we have an sp3 hybridized carbon in between them. So these two p orbitals cannot overlap now because they're too far apart, and there's a carbon in between, so they just can't overlap. And notice in our accumulated system, we have all these p orbitals, but as I mentioned, this sp hybridized carbon has a p orbital in the up above and below this plane indicated here, and the other p orbital is within that plane, so they're orthogonal to each other. And these pi systems can't communicate, neither can these pi systems. But in this one, we have one conjugated pi system. The electrons can just move about unrestricted between all four of those carbon atoms. This is just to show the structure of alene. If we were to do something like get an X-ray crystallograph of crystals of this alene, which would be a little bit difficult. We'd have to have very cold temperatures. But notice that these two methylene groups are perpendicular to each other. If we rotate this and look down the plane, we can see over here that they're perpendicular. Okay, the two pi bonding MOs are in perpendicular planes. But we're more interested in the conjugated systems. So let's now think about this. We're using valence bond theory. We have our hybridized carbons, and we have two carbons that are connected to each other. We could have 6 different kinds of carbon-carbon bonds. We could have 2 sp3s, or we could get all the way down to 2 sp hybridized carbons bonding to each other. And as it turns out, as we go from sp3 bonded to sp3, that's the longest of the carbon-carbon bond lengths. And when we get down to the sp bonded to another sp carbon, it's much shorter, only 138 picometers as opposed to 152. So let's take a look at this, and we're going to talk about why. Let's think again about hybridization. So when we hybridize our orbitals, we mix them. The electrons in s orbitals are held more closely to the nucleus than electrons in p orbitals. So when we make orbitals from these things, the hybrid orbitals are constructed by mixing s and p orbitals. Thus, the more s character in a hybrid orbital, the more closely the electrons are held to the nucleus. The length of the carbon-carbon sigma bonds is dependent upon the hybridization of the carbon atoms. So if we have an sp3 hybridized carbon, that means we made it from the s orbital on carbon, the 2s orbital, and the 2p orbitals were all mixed together to make 4 new orbitals that we called sp3. Each one of those orbitals has what we call 25% s character, because we had 1 s orbital and 3 p orbitals. In an sp2 hybridized carbon, we take the s orbital, the 2s orbital, and 2 of the 2p orbitals and mix them together. So the sp2 hybridized carbon has 33% s character, because it's only 1 of 3 orbitals that are used to mix. When we have sp hybridization, we have 50% s character. So that explains that the more s character we have, the more tightly those electrons in the hybrid orbitals are held to the nucleus, and the bonds become shorter. So, are conjugated dienes more stable than unconjugated dienes? So we can take a look at this experiment where we do the hydrogenation of these two compounds, and the product is the same. So whether we hydrogenate this isolated pi system or this conjugated pi system, we get the same outcome, the same product is formed. And if we take a look at the heat of that hydrogenation, it'll tell us a little bit about the energy levels. Because these two products are the same, they're at the same energy level. And we find that when we do the hydrogenation of the isolated carbon diene system, we get 255 kilojoules of energy is evolved during the hydrogenation. But the conjugated diene, there's 29 kilojoules less energy is evolved, only 226 kilojoules per mole. So that's telling us that it's lower in energy. The conjugated system is lower in energy than the non-conjugated system. So is that stabilization due to the conjugation? Now, some of you might recall that the more substituted a double bond is, the lower in energy it is, the more stable it is. So in this particular instance, one of our double bonds is more substituted than the other. So maybe that is why we're getting less heat evolved in this hydrogenation reaction. Okay, so that's our more substituted double bond is right there. Recall the relative stability of alkenes. The more substituted our double bond is, the more stable it is. So when we have a tetrasubstituted double bond, it's considerably lower in energy than when we don't have any substituents on the double bond. Now by substitution, in this case I'm talking about alkyl substitution. So we get this lowering of energy. This data is from a series of hydrogenation reactions of these different compounds. Notice that these three compounds will give the same product. These other ones won't. So there had to be a lot of different experiments done to actually come up with this series of energies, but three of them have the same product, so we can compare them directly, and that is the the terminal double bond and the internal double bonds can give those same series. Once we get branching here on the disubstituted at one carbon, the trisubstituted and the tetrasubstituted, our reactants give different products. But for those ones that give the same product, we can see that we do get this stabilization. That is, the terminal one is the highest in energy. As soon as we have an internal bond, it lowers by about 7 kilojoules per mole for the cis disubstituted compound, and even 5 kilojoules per mole further for the trans-substituted compound. One of the experiments that was done then to try and suss out whether or not this conjugation gives us added stabilization was to do the hydrogenation of two of these terminal alkenes and the hydrogenation of one of this conjugated alkene, but as terminal groups. So the substitution pattern is the same on them, and we do see that we get about 15 kilojoules per mole stabilization in this system. Another similar experiment was just, here we see it in a graph where we hydrogenate two double bonds in this instance. Notice that we have to use twice as much of this compound because we have two double bonds on one molecule over here. But it should give the same results, and we do see that we get that the isolated double bond is a little bit higher in energy by about 15 kilojoules. Another similar experiment was done. In this case, they hydrogenated one pentene and two pentene, sum that up and divide by 2, and we see that when we do the hydrogenation here, so that again we have a terminal double bond on this one, and we have an internal disubstituted double bond here, so that they're the same. We get this 15 kilojoules of mole difference. So we attribute that the stability of the conjugated system is a little bit more. We attribute that 15 kilojoules of stabilization energy to the conjugation. So there's a lot of different conjugated systems in nature and man-made. The other thing that you'll notice is when you have lots of conjugation, you begin to get colored compounds. We'll talk about that a little bit later. So here we see up here, this is lycopene, and it's a highly conjugated system, and that's responsible for the red color in tomatoes. Resonance can explain this conjugative stabilization. We've discussed this numerous times. We can show the resonance. Here we have a conjugated carbocation. We have a double bond here. There's p orbital there, p orbital there. They're sharing a pair of electrons. This carbocation is also sp2 hybridized, so there's an empty p orbital there. And we can delocalize our electrons through through resonance, so that the positive charge is shared between this carbon and this carbon. Roughly 50-50%, although this particular contributor would contribute a little bit more because it's secondary-like, and this one is primary-like. Remember, this is not a primary carbocation, nor is it a secondary carbocation. We call this an allyl carbocation because it's delocalized. The charge is both here and here. close to 50%. We can also delocalize radicals. Notice now we're using the fishhook type of arrows because we're moving one electron at a time as opposed to moving a pair of electrons here. But we could do experiments and we can find out that that electron resides here, here, and here all at the same time. It's delocalized over those three positions. And we can show the different resonance forms where we see that the electron can exist at each of those three carbon atoms. A conjugated system involves at least one atom with a p orbital adjacent to at least one pi bond. So when we have a conjugated diene, remember these are all sp2 hybridized, so we build the pi system by the overlap of those p orbitals that remain on those carbons. So here we have a p orbital, and we have another p orbital next to that double bond. In this case, that's a p orbital that's also conjugated with this next carbon. So we have 4 p orbitals in a row here. And our allylic, the allylic system has a double bond. It's a 3-carbon system. Has a double bonded carbon, and then over here it has a carbon, in this case with a lone electron in it, not a lone pair of electrons, but a single electron. This is a radical, and that electron is delocalized over all 3 of those carbon atoms. The same thing with this allylic atom. That positive charge is delocalized over those 3 carbon atoms. And even the allylic anion, now we have 4 electrons in our pi system, and that negative charge is delocalized over all 3 of those carbon atoms. So one of the questions we might ask is it conjugated? We've seen already that this is conjugated. We have carbon-carbon double bond separated by a carbon-carbon single bond. That's conjugated. This one is isolated, and it's isolated because we have an sp3 hybridized carbon in the middle between those 2 different pi systems, so the electrons can't delocalize from one pi system to the other. Now, if we look at these, we may think that they're not conjugated, but they are conjugated because we have a pi system here, a pi system here, and our carbocation is sp2 hybridized and has an empty p orbital on this carbon, so all 5 of those p orbitals can line up. The same thing happens here with our negatively charged system. We think about this as being sp2 hybridized because it stabilizes by the fact that if it is sp2 hybridized, it can become conjugated with these other 2 pi systems. So that negative charge would spread itself, and we would find that it would exist on the 1, 3, and 5 positions all at the same time. Remember, resonance is not an interconversion of the resonance contributes. It's a hybrid of all of the resonance contributors. Okay, so the same thing happens here. We think of oxygen, those 2 lone pairs of electrons on oxygen can exist in a p orbital, and if they exist in a p orbital, in this instance, that p orbital would be conjugated with these 2 pi systems, so it's energetically favorable for it to be sp2 hybridized with a lone pair of electrons existing in this entire pi system. They all have resonance forms. We can draw resonance and delocalize that charge. Now, if it's bound to 4 atoms, it can participate in conjugation, but neither, in this instance, these are not conjugated because we have sp3 hybridized atoms in the middle that cannot have, they have no p orbital that they contribute to the pi system. So we now can throw this into our relative carbocation series. Vinyl carbocations are very unstable. Primary we also talk about them as being pretty unstable. Secondary are pretty stable. Next instability is the allylic type of cation, and then we get our tertiary cations. And this one, also allylic, is slightly more stable because one of the resonance forms that we can draw is tertiary-like. We could draw the other resonance form that shows a positive charge on this carbon. It would look like a primary carbocation. This resonance would contribute considerably more to the real structure of this carbocation than the resonance structure which has the positive charge on the terminal carbon. Okay, so now we're used to the theory that we typically are thinking about when we draw these Lewis structures is valence bond theories. What we're going to ask now is, can we use molecular orbital theory to explain conjugation and its stabilization? So a molecule or part of a molecule where each atom has a p orbital that is in the same plane. These are all in the same plane. They're sticking up above the plane. They can communicate. This allows the electrons to move across all of those p orbitals, making the molecule more stable. So let's think a little bit more about molecular orbital theory. A complete description of even a simple molecule like ethene looks daunting. Okay, look at all of these different orbitals that we have to construct. It's a little hard. We haven't done that too much unless you took your class from Dr. Ellis on inorganic chemistry. He does some work on forming molecular orbital systems, so some of you chemists are familiar with that. There's a lot of work that you have to do to get there. But notice that our highest occupied molecular orbital and our lowest occupied molecular orbital, our lowest unoccupied molecular orbital, they're just a simple pi bond that we use to describe what a alkene system looks like. So let's extend this. So even though this is daunting, we only need to describe the pi system, and we can do that on top of the Lewis structure valence bond framework that we've been using all along, that we're used to looking at and discussing when we talk about reactivity. So remember how we built pi orbitals, okay? We built pi orbitals by overlapping of a p orbital from one carbon with a p orbital from another. We mix them to make our bonding molecular orbital, and we mix them in an anti-bonding way as well, or we subtract them, whichever you care to talk about. But this then becomes our pi star orbital, and this is our pi orbital. When we take the electrons that were in those p orbitals, we can put two electrons in one orbital. Both of them are in lower energy, so we say that this is a bonding molecular orbital. And we have no electrons in that higher energy anti-bonding molecular orbital. If we did, because it's anti-bonding, it would start pushing the nuclei away from each other. Carbonyl system is similar. We build our pi system in a similar fashion. The only difference is that the p orbitals from which we build our pi system are a little bit lower in energy because of the electronegativity of the oxygen atom. There's more protons in the nucleus, and they're stabilizing that negative charge in that electron. They're pulling that down. But we can still, they're still energetically favorable enough to overlap to build a pi system. And we talk about the pi system that it builds. We show the electrons are in this bonding pi orbital, and it has a slightly higher lobe on the oxygen because there's going to be more electron density near the oxygen because of all those protons in the nucleus of the oxygen are pulling those electrons to it closer. That's why oxygen's more electronegative. So we say that the p orbital from the oxygen contributes more to the molecular orbital than the p orbital from the carbon. Now the exact opposite occurs in the anti-bonding orbital, but we needn't worry about the anti-bonding orbital, at least not yet, because there are no electrons in there. You'll often see different ways of depicting these. Sometimes you'll see carbon-oxygen pi system shown like this, just the overlapping p orbitals. Sometimes we may take some artistic license and construct our orbitals, and we would have a little bit bigger lobe on the oxygen than on the carbon. So recall our diene systems. The cumulated diene system cannot communicate because they're at 90 degrees to each other. The isolated diene system cannot communicate because we've broken up the overlap of p orbitals by sticking in an sp3 hybridized atom in there. That cannot contribute a p orbital to the pi system. And our conjugated system is completely able to communicate because the p orbitals are just one bond apart and they all line up in a planar fashion. Okay, so we're going to talk now about building conjugated molecular orbitals. Once we build molecular orbitals from atomic orbitals, we can then combine them to make larger molecular orbitals in the same manner. So once we take our two carbon atoms, sp2 hybridized, and we take the leftover p orbitals to construct a pi bonding orbital and a pi anti-bonding orbital, we can now take those two systems and add them together just like we did from the atomic orbitals. So we can take molecular orbitals. In this case, we're taking these two molecular orbitals and we're combining them in a bonding fashion. Notice how the phase is all the same. So this phase lines up with this phase. We can also mix them together in an anti-bonding fashion, in which case there's a change in phase on going from this carbon to this carbon over here. So this is an anti-bonding orbital, at least relative to this. Now notice that this particular series of orbitals, of atomic orbitals contributing to the molecular orbital, these two have the same phase, so they're interacting in a bonding fashion. The next two there's a change of phase as we go from one to the other, so they're interacting in an anti-bonding fashion. And then the last two are also interacting in a bonding fashion. So if you think about it, we have two bonding interactions and one anti-bonding interaction. So this is an overall bonding molecular orbital. We can also then combine these orbitals in a similar fashion to make two new orbitals. And now let's go across and notice that up here we have an anti-bonding interaction when we go from carbon 1 to carbon 2. From carbon 2 to carbon 3, we have a bonding interaction. And from carbon 3 to carbon 4, we have another anti-bonding interaction. So in this case, we have two anti-bonding interactions and one bonding interaction. So this one has a net anti-bonding interaction. In some ways, so this would have a bond order of 2. This would have a bond order of 1. This one would have an anti-bonding order because we have more anti-bonding interactions than bonding interactions. And this one up here is all the interactions are anti-bonding interaction. And that just means that we change phase as we stay on the same side above that plane. We change phase on going from one orbital to the next. Okay. Note that the node of zero electron density occurs in the region where a change in phase occurs. So in this first orbital, we have no nodes other than the planar node that's in all of these molecular orbitals, but there's no node as we go from left to right. In the next higher up orbital, we'll call this pi 2 orbital, we have a probability of 0 of finding an electron in this particular region. There's a node between here and here because there's this change inside. Now the next higher up orbital, we have 2 nodes and then 3 nodes on going from left to right. So that's important. You always will increase the number of nodes by 1 as you go from bottom to top, as you go from lower energy to higher energy of these orbitals. So MO theory offers an alternate explanation why the central carbon-carbon single bond is shorter and stronger than a typical carbon-carbon single bond. The 4 electrons in butadiene will occupy the lowest energy MOs, and so we put them in here, we have all bonding interactions. Then we put them up here, and we have bonding interactions between these two carbons. So the phase, no double bond character because the phase at C2 and C3 do not constructively overlap. But we do have double bond character between the phases at C2 and C3 in the Psi1 orbital. In this case, we've named them slightly differently. So here we see the MOs. These are just different representations for the same thing. We often will just use an array of p orbitals to describe an orbital. So notice that over here we have an array of p orbitals that are all lined up on one side. Over here we've kind of combined it to show what it looks like probably a true molecular orbital, but we can represent it by using over here. This is easier for us to draw for those of us that are not very artistically inclined than to try and draw these orbitals over here. So most of the time, chemists will just use this kind of representation to talk about molecular orbitals. You may see ones that look a little bit different because they're computer generated or the person making them has more artistic ability than I do. So these are just two slightly different representations for the same thing. The pi molecular orbitals for the butadiene system, a 4-carbon system that's conjugated, so the p orbitals line up. We can extend this out to infinity if we want. And the nice thing is, because of that symmetry that we talked about earlier, so we have a p orbital. Here we have just a regular pi system. As soon as we get to 3 p orbitals in a row, we can talk about conjugated system. So this is a conjugated system. And notice now that we have no change in phase here. Notice also that in this system, there's kind of a node here. This is neither bonding or anti-bonding. Arguably, it's anti-bonding because you're changing phase. However, they're too far apart to have any structural overlap between those two orbitals. So it's actually what we call a non-bonding orbital. And up here, this is anti-bonding because all of the interactions are anti-bonding. In the next one, the 4-carbon system, again, all bonding interactions. Here we have one more bonding interaction than anti-bonding interaction because we have 2 bonding interactions between p orbitals, that between C1, C2, and it's bonding between C3 and C4, but the interaction between C2 and C3 is anti-bonding. This is still a net bonding orbital. As soon as we get above that line, above the non-bonding energy level, we see that we have more anti-bonding interactions than bonding interactions. So everything above this line, which is at the non-bonding level, is net anti-bonding, and everything below it is net bonding. Notice as well that all of our odd-numbered systems, so we have 1, 3, 5, or 7 atoms in a row with p orbitals left over, that we have these big gaps in between and that they're non-bonding. So here we see the system for 1,3,5 hexatriene. Again, 2 different representations. This is the one that's probably easiest for us to draw, and this is the one that would take some artistic ability to draw or some sophisticated computer graphics. You also may sometimes see systems that look like this. This is another representation. In this representation, we're kind of looking at the system from the top. We're looking at it from above rather than from the side-on view that we are with these systems over here. Okay, so we see that this double bond is 137 picometers, and these carbon-carbon single bonds 146. So the distance between these 2 carbons is slightly more than the distance between the ones in which we've drawn the carbon-carbon double bonds. You can sum up all the interactions and come to that conclusion. So this is just a written description of how we would go about building our the symmetry in our system. So if you're having some trouble, take a look at this. The next thing we're going to be considering are reactions of these systems, of any systems actually. When we have a reaction between two chemical species, it is the electrons that are in the highest energy orbitals, the highest occupied orbitals, that are the most important in terms of the interactions between the two molecules. Reactions that molecules undergo can often be explained by studying their frontier molecular orbitals. And those are the orbitals that are, the occupied ones are highest in energy, and the unoccupied ones are lowest in energy. So we can get an interaction between the highest occupied molecular orbital of one molecule and the lowest unoccupied molecular orbital of another molecule. We can also see that we could put in some electromagnetic radiation in the form of light. If we exactly match this energy level, we can promote an electron from one orbital to the next, so long as our photon that we put into the system exactly matches that energy level. We can promote an electron up to a higher excited state. And these molecules, once we do that, are typically more reactive, and we can do things by putting the energy into our system with light rather than heat. Okay, so we have we've talked already about the highest occupied molecular orbital. Let's just go back one. That would be this orbital right here, because it's the highest energy orbital that has electrons in it, at the highest occupied molecular orbital. The one above it has no electrons in it. That's the lowest unoccupied molecular orbital. This orbital here is also unoccupied, but there's a lower unoccupied orbital below it. So these are the orbitals that are important when we really want to describe what's going on chemically between a pair of molecules. Sometimes we'll just have a single electron in an orbital, and we call that a singly occupied molecular orbital. This is what happens when we have things like radicals. There's one electron in an orbital. It's a singly occupied molecular orbital. It can also be, typically is also the highest occupied molecular orbital. So it can be both. The SOMO is also usually highest occupied molecular orbital. Now let's take a look at the allyl system. This is the 3-carbon system, which in valence bond theory, and we'll see this in just a second, we use resonance to describe what's going on. But we don't need to. We can use molecular orbital analysis just as easily. Okay, so here we're looking at an allyl radical. How many electrons are we talking about in this pi system? Well, we can count them. There's going to be 2 in this carbon-carbon double bond, and we see just a single electron over here on this CH2 group at the end. So we have 3 electrons in this system. Once we make our orbitals, we put our electrons in. Remember, we put an electron in the lowest energy orbital, and then we keep filling. If there's any orbitals of the same energy, we fill them one at a time before we put the next electron in and pair the spin. So here we see a spin up and a spin down electron. We don't have any degenerate orbitals. We only have the one orbital. So we put our first electron in, then we put a flipped spin second electron in. So we now have an electron pair in there. And then we put our third electron in to the next lowest unoccupied orbital. Then we put it in there, and we see here we have the allyl system. Okay. Now, if we remove an electron, it's going to come out of the highest occupied molecular orbital because that's the easiest one to ionize, and we could promote this electron right out of the molecule, and then we get a carbocation. In this instance, notice the carbocation now, there's only 2 electrons in it because we have a positive charge over here on this electron. On that carbon atom. So if we take, this is just another representation of the allyl system and how we can build it. We can build it the same way using our linear combination. We can build our pi system on 2 orbitals, and then we mix those with the p orbital from the other atom that we hadn't done yet. And notice the mixing's a little bit different. Don't get too concerned about this. We're not going to be constructing too many. And as long as you know the easy way to build the extended systems, you'll be okay. Okay. So the allyl anion. Look at this allyl anion. Let's count the electrons in this allyl anion. We have a carbon-carbon double bond. There's 2 electrons in there. And over here, we have carbon, and there's 2 electrons in here, because if there was only 1 electron in there, it would be a neutral molecule. Because it's a negatively charged compound, we have to put an additional electron in, so we have 4 electrons. So you have to be a little careful here. When you have an anion, you have to remember that the neutral system would be a radical, so that we have to add an additional electron when we do our count. So we have 2 electrons in our pi bond, our double bond, and we have 2 electrons because we have to have 1 to form the radical and the second electron to make it an anion. If it were a cation, there wouldn't be any electrons on that resonance structure that we're drawing right there. Okay, so once we see that we have 4, here's the orbitals we made with the orbital energy levels, and we just fill them up. 1, 2, 3, 4. So let's take a look at something like methyl vinyl ether. Okay, so this is methyl vinyl ether. We have an sp2 hybridized carbon-carbon double bond, and then we have the oxygen, and we have electrons in one of the p orbitals of the oxygen right next to our pi system. So we can think of this as being a conjugated system. It is a conjugated system. Now, typically, we could describe this, and we often talk about resonance structures and the fact that this oxygen can donate its electrons into this pi system, and we could have this zwitterionic resonance contributor. We could easily see that this contributes to some extent because they're conjugated. When we talk about the molecular orbitals, notice now what we see is that we have our lowest energy level has 2 electrons in it, and it is this molecular orbital where all the phase is the same when we go from left to right or right to left and stay above the plane of our system. The next energy level, we have a node here, and we have a big gap. So we have, in this case, 2 electrons from the oxygen p orbital contribute, and we see that we have some electrons in there. And then our last energy level is unoccupied. So this is the molecular orbital description for the methyl vinyl ether system, pi system only. Okay, and this is our resonance valence bond description for the same thing. Okay, so these are just 2 different models, slightly different models that we can use to talk about the chemistry of these things. As it turns out, they're not as different as we think. If we continue to apply the theories that were added, or this theory has evolved, and they actually give the same answers. So they're not that different. It's just how we start them that is that different. Okay, so inductive versus resonance, the importance of pi donation. So if we take a look at methyl T-butyl ether, it has a significant dipole moment. Because oxygen's more electronegative than carbon, we get this inductive effect from the oxygen just in that carbon-oxygen sigma bond right there. It's got a little bit of a dipole, and as it turns out, methyl T-butyl ether, there's the methyl group, there's the T-butyl group, is a little bit more polar than we might expect, and in fact it's quite soluble in a water system, much more than we would anticipate. If we exchange that for a carbon, it wouldn't be soluble very much at all because it wouldn't have that dipole moment. But when we put the oxygen there, we get this inductive effect that happens. Okay, so the oxygen inductive effect, its electronegativity is very important here. Having said that, if we were to remove one of these hydrogen atoms with its pair of electrons, okay, we would end up with a carbocation. That carbocation is considerably more stable than we might expect because the electrons that are in the p orbital of the oxygen line up with the p orbital in the carbon, and we can get this donation. So oxygen has dual competing pathways. Inductively, it's electron withdrawing, but through resonance, it's electron donating. Okay, so we could draw this structure. We say this is the best structure because the octet rule is obeyed. Oxygen has 8 electrons around it. We could show another resonance structure with an oxygen-carbon single bond and a positive charge on the carbon. So that charge is delocalized over the oxygen and the carbon. Okay. Now the same thing doesn't apply in this instance. Chlorine is inductively electron withdrawing. We have a dipole in chloroform. It's a polar molecule. If we were to pull a hydrogen with its electrons off and get this carbocation, the chlorine overlap is not as good because the electrons in the p orbital of chlorine are in a 3p orbital, and the p orbital that's vacant on the carbon is a 2p orbital, so we don't get proper energetic overlap, and so we don't get good spatial overlap. Take a look at that. That's not too important most of the time. Periodically, you'll run across it. And I think we'll end there for today.